Hello, I'm Nathaniel and today we will now do question 8 of STEP 2021. This is the most technical question in part 1 of STEP 2022, paper 2. And why do I say part 1? It's because there are 3 parts in here. There's pure maths, there's mechanics, and there's statistics. Got that sorted out? Ready? Now, let us figure out why this question is so technical. Here's my pen. Great. So, on this question, you need to do a double differentiation and an integration. And this question is called a reduction formula in the further maths syllabus. So, how are we gonna do this? Well, it's simple. But first, you need to know 2 formulas. Actually, 1, because then you can derive the other formula. The derivative of a product of functions fx, gx equals to f prime g plus g prime f. Do you understand what's going on now? So everyone gets a turn to be primed. That's basically the product rule, how I remember it. So why do you say we can derive the other formula? So fg equals to the integration of f prime g plus g prime f dx. And you know the sum rule for integrals, right? You can just put the integral here and do here. So this means that fg prime integral fg prime dx equals to fg minus f prime g dx. Now, does that make sense to you? Oh, and don't forget the signs. We're supposed to put a minus here, and a plus here. So this means we take negative on both sides. This will be important later when we have to integrate many products. There, we have just derived the integration product rule, also known in further maths speak as integration by parts. I don't know why it's called that. I'm just trying to tell you that this mathematics notation or nomenclature is really bad and we better change it. Anyways, but now's not the time to change mathematical nomenclature and notation. Now is the time to solve a step question. So we're just keeping the 2 formulas here just in case you have to refer to them. And what I'm going to do is that I am going to box them, because that seems like the most legit thing to do, right? So you remember when I was in the exam, I couldn't remember all the circle properties. Obviously it's E mathematics, and so I wrote them all down and I boxed them. Simple and easy as pie. Actually easy as 3.14, but who cares? Let's just solve the question. So to find the second derivative, we have to find the first derivative first. D over dt, tn, 1 minus tn, and then everyone gets a term to be prime, right? And tn minus 1, 1 minus tn, but there's no plus here, instead it's a minus. Why? Because there's already a minus in the bracket, which makes things effectively easier for all of us. So n, obviously the n comes from the 1 minus e to the power of n, ntn 1 minus tn minus 1. There, we have effectively found the first derivative. And just so in case we will have to simplify it, so ntn minus 1, 1 minus tn minus 1, 1 minus t, and then this can be simplified to 1 minus 2t. Now, we will have to use this simplification later on. Now, we have to find the derivative of this, since it's the second derivative, not the first derivative. So d squared over dt squared equals to, so we use the unsimplified variant, and now we have a double product rule. How? Simply, how do we do this? So since 2 of the terms would be the same, they just are. So first we have to simplify n minus 2. And don't forget, we have an n minus 1 supposed to be here. And then we have to put minus 2n squared n minus 1, 1 minus tn minus 1. Why 2? It's because you can derive that term in both ways. As you can see, you could differentiate this, or you could differentiate this, and either way you still get the same term. This is why we have a 2. So, and then we have n minus 1, t n1 minus t n minus 2. There. And now comes the great big algebraic simplification. I know that most of you might not like algebra, but I'm just going to walk through everything for you just to make everything easier. Now we have to factorize nt n minus 2, 1 minus t n minus 2, and then n minus 1. And since there are two terms with n minus 1, so this is t squared plus 1 minus t squared minus 2n t 1 minus t. Now we are now going to expand. So n minus 1, 1 minus 2t plus 2t squared minus 2nt plus 2nt squared. Now this is where it gets real interesting, and I mean it. So nt n minus 2, 1 minus t n minus 2, and then n minus 1 minus n minus 1, actually plus, so 2t squared minus 2t, and then we have another n minus 1. Instead of having an n minus 1, we have an n 2t squared minus 2t. So we can actually simplify that term to become, we'll see later, n minus 1 minus 2, 2n minus 1, since we added, and then t 1 minus t. And effectively, we have solved everything. And now we're 7 minutes into the video, and I don't know why this has taken so long, but just for the sake of your learning, I have figured out all the simplification steps already, and I walked through all of them in this detail. So please forgive me if this video is extremely long, as it's my job to make everything easier for all of you math students, right? So we'll put the d over dt squared somewhere. Obviously, the somewhere is in front of the d squared over dt squared sign. There. So the sequence t0, t1 is defined by this. So we have already solved this question. Now let us delete it. The sequence t0, t1 is defined by this. So that when n is greater than 2, tn equals to tn minus 2 minus 2, 2n minus 1, tn minus 1. Now this may seem obvious to you, but again, for the sake of your learning, let us do the integration by parts. As you can see, this integral, the reduction formula bears a similar resemblance to d squared over dt squared, and we will see exactly why this is the case. So this is actually a very simple integration by parts. We encounter more complicated things in the further math syllabus, but we're just going through it so that I can help you. So remember the integration by parts formula up top. You see integral f g prime dx. So we need to find f and g prime, or we usually write it as u and v. So u is tn y minus tn, and then du over dt equals to, let us check our results. Let's use the simplified form. And then this means that we now have to find dv over dt equals to et over n factorial, and this is easily integrable, and it becomes et over n factorial. This is what happens when you integrate or differentiate exponential functions. Get it? Okay, now you have to find uv. So tn equals to, in integration by parts, you also had to take into account the limits, which are this 1, 0 minus the integral of nt n minus 1, 1 minus t n minus 1, 1 minus 2t et over n factorial dt. I do a lot of these reduction formulas, so I'm quite competent at this. So we have effectively found tn, but not so fast. We can simplify this a bit more. This, you see, it has limit points at 1 and 0, and either one of these is going to be 0. So let us take away this term. Sorry, excuse me, I just burped. Great. And so we can deduce further that Tn would now be equal, Tn equals to, and u will be this, and then du over dt will be that monstrous thing we saw earlier. That. So, this will be Ntn minus 2. Actually, you see the monstrous thing up there? We do not need to put in the definite integrals, because when the limit point is 0, t will be 0, and then when the limit point is 1, 1 minus Tn minus 2 will be 0. And therefore, the integral would therefore be 1, 0, Ntn minus 2, 1 minus Tn minus 2, n minus 1, minus 2, 2n minus 1, t, 1 minus t, et over n factorial dt. Now we can simplify this. The moment you'll be waiting for, let us simplify what we need to do. So n minus 1 would then simplify the bottom to be n minus 2 factorial, n minus 2 factorial, so this will be t n minus 2, 1 minus t n minus 2 et, and then minus 2, 2n minus 1, and then the n will turn the bottom to n minus 1 factorial dt, and then 2n minus 1 et tn minus 1, 1 minus t n minus 1. Now do you see how the reduction formula gets found? And then we can happily simplify it using the sum rule for integrals, which is basically the sum of the integrals to the integral of the sum. And then this will become tn minus 2 minus 2, 2n minus 1, tn minus 1. And you have made it this far. Congratulations! You have just passed the hardest bit of the question. Let us delete our results and neaten everything, because this is our custom to do in math exams, although we don't usually delete our workings. We just write them in a little answer box. Get it? So, just giving you a bit of math culture here. And here is our result. And now we can delete our u's, du's, v's, and dv's all the way up here. And then we can delete this. Now, evaluate t0 and t1 and deduce this. So, we found Tn, we can remember that Tn equals to integral 1, 0, Tn 1 minus Tn et over n factorial dt. So evaluate T0 and T1 and deduce this. T0 equals to, obviously this will be 1, and so et 1, 0, because 0 factorial would then be 1. Then this will be e minus 1. T1 needs a bit of work. 1, 0, T1 minus T et dt. Now, at first thought, you might think that this might be a very strange integral to work with, as we had to do a triple integral by parts. This is not the case, as you'll see here. And then we just had to do integration by parts on these two components. This one's easy. So integral T et dt equals to T et 1, 0 minus 1, 0 et dt equals to 1. Because this will be e, and then this will be 1. This will be e minus 1, and so the e's cancel out, leaving us with 1. So 1, 0 t squared et dt equals to t squared et, more integration by parts, and you can figure out what the u's and v's are. Congratulations. T et dt equals to, then this means t squared et will then be e minus 2. So this means that t1 equals to 3 minus e. And since t0 and t1 are linear combinations of e and a separate integer, this effectively means that an and bn are integers, and tn can always be written in this form. So we can write tn equals to a linear combination of e minus 1 and 3 minus e, or 1 and E. So if you want to learn more about this thing, you can Google up basis vectors and you will get into ranks, which is the type of thing they use in the further maths syllabus before I took the further maths exam. It's a very interesting topic and it talks a lot about this linear combinations thing. And you also want to look up more integral linear combinations, as in integer linear combinations. You can look up the Euclidean algorithm to find out whether one can be written as a linear combination of two more numbers. It turns out that if the two numbers that you want have no common divisor, then you can write one as a linear combination of those two numbers, and which implies you can write any number as a linear combination of all these numbers. Now that's a very deep topic. So show that 0Tn e over n factorial. So for 0T1, 0Tn 1 minus Tn less than equals to 1, 0 et e, so this means 0 Tn 1 minus Tn et over n factorial. You can really multiply these limits, is less than or equal to e over n factorial. So this means that 0 less than Tn less than e over n factorial. Therefore, an plus bne less than 0 as n is to infinity, and then negating an over bn equals to e. Actually not equals to e, but it tends to e. Now I can see, and I bet all of you can see, a possible application for this question is when you want to find approximations to e. So you can run this on better and better approximations with higher and higher values of n. Then congratulations, you have found e to quite a lot of digits, and those digits of e are yours. Okay, see you in another maths video.